Okay, welcome to our new episode. And today I will be discussing to you the different gas laws. The slides is downloaded from the website islevenschemistry.weebly.com uploads. So this is a good PowerPoint presentation, so I decided to use it for our gas laws discussion. Before we can discuss the gas laws, let us try to discuss first the characteristics of gases. So when we say gases, they are highly compressible. Unlike solids and liquids, gases can be compressed. Okay, liquids can be compressed, but gases are more compressible than solids and liquids. Also, gases occupy the full volume of their containers. So when you put gases on a container, it follows the volume and the shape of its container. Also, gases exerts a uniform pressure on all inner surface of a container. So if you have a spherical container, the pressure of the gases inside the spherical container is uniformly distributed, same pressure all throughout the surface of that container. Also, gases diffuses or mix easily and quickly. We know that when somebody is wearing perfume, we can easily smell it because it diffuses or mixes in the air very quickly. And of course, gases have very low densities, shown a while back. Okay, and we have this equation here. Okay, this is 0 Kelvin. This is negative 273 and negative 459 degrees Fahrenheit. You can actually see the relationship of these temperatures here using the equation that I gave you. For example, if I were to put if you are to ask how many Kelvin are there in 0 degrees Celsius, so of course if you put 0 in here, it would be 273. So the illustration really tells us that 0 degrees Celsius is equivalent to 273. Okay, and that's also same way you can do that also to the different temperatures here and the different temperatures here. Okay, so when you try to calculate 0 degrees Celsius to Kelvin, okay, you use the equation that I gave you kanina, it would give you in here 273. You can do that also to the other missing temperatures here. For example, if we have 100 degrees Celsius and you want to convert it to Kelvin, according to the equation a while back, it's just degrees Celsius plus 273, so you would have 373 Kelvin in here. Okay? Yan, so answers, absolute zero is 0 Kelvin or 273 degrees Celsius. Okay? You may want to practice solving these conversions here. You may pause this video and try to convert, but your computation should have the following answers. Yan. And which shoes create the most pressure? Of course, you may want to compute first the the force applied on those shoes and the area that they occupy. And then you divide the force applied over the area they occupied, and that would give you the pressure. And you may compare the pressure that is given by these objects here. Okay. So there are some key units at sea level. We have 101.325 kilopascal or 1 atmosphere, or 760 millimeters mercury, 760 torr, 14.7 psi. Ibig sabihin yan, 1 atmosphere is equal to 760 millimeter mercury, 760 torr, or 101.325 pascal, or if you try to move the decimal place, it would give you 101.325 kilopascal, which is just the same with this. Okay. And so the barometer is a device that measures atmospheric pressure. Yan ang ginagamit natin. This is a Mercury Barometer. Okay. And we have also here an aneroid barometer. These are devices that measures pressure or atmospheric pressure. When you see the acronym STP on problems, that means standard temperature and pressure. The standard temperature and pressure is 273 Kelvin and 101.325 kilopascal. Also SLC, or standard laboratory conditions, that's 25 degrees Celsius or 298 Kelvin and 101.325 kilopascal. And 101.325 kilopascal, I should say. Now, having those concepts, let us try to discuss or understand the gas laws. I will be discussing to you the Boyles Law, the Charles Law, and the Galos X Law. Let us try to discuss first the Boyles Law. The Boyles Law is postulated by Robert Boyle, and according to this law, the pressure and volume of a gas are inversely related at constant mass and temperature. So, the pressure and volume are inversely related or inversely proportional. This means that if the pressure increases, the volume decreases, and vice versa. If the volume decreases, pressure increases. If the volume increases, pressure decreases. That's what inversely proportional means. Okay? So, if we have this relationship, it would tell us that the product of the pressure and volume of a gas at initial condition should be equal to the product of the pressure and volume of a gas at the final condition. This will give us to the equation of Boyle's law, which is P1 multiplied by V1 equal to P2 multiplied by V2, or the product of the pressure and volume at initial condition, denoted by the number 1, is equal to the product of the pressure and volume of the gas at its final condition. This illustration in here tells us the relationship of volume at the y-axis and pressure at the x-axis. For example, at pressure, which is 100 pascal, the volume of a gas shown in here is equal to 20 meter cube. If you are increasing the volume to 200, the pressure is doubled, you will observe that the volume of the gas is also reduced from 20 meter cube to 10, or that's half of the initial condition. The volume increases by, the pressure is increased by 100%, and the volume is decreased by also about half the original volume. This really shows that volume and pressure are inversely proportional. It is also being illustrated by the cylindrical object in here. When the volume is decreased, then the pressure is increased. Okay. I have here a problem. It says a sample of chlorine gas occupies a volume of 946 ml at a pressure of 726 millimeters mercury. What is the pressure of the gas in millimeters mercury if the volume is reduced at constant temperature to 154 ml? So this is in terms of volume, 946 ml is in terms of volume, and 726 millimeters mercury is in terms of pressure. So these are the initial conditions of the gas, and 154 ml is the final condition of the gas. So if you try to observe 946 and 154, the final condition tells us that the gas is being compressed. So we are tasked to compute for the final pressure. So we use the equation pressure 1 multiplied by volume 1 is equal to pressure 2 multiplied by volume 2. We are given pressure 1, okay, to be 726 millimeters mercury and a volume of 946 ml. We are asked to compute for the final pressure if the volume is 154 ml. So P2 is being asked. Okay, so by simple manipulation of equation, okay, we may divide V2 from P1 and V1. So P1 multiplied by V1 over V2 should be equal to the pressure at the final condition. So putting the given to the different symbols, it would give us 726 millimeters mercury times 946 ml divided by 154 ml. The unit of the volume will cancel out, leaving us millimeters mercury, which is the unit of pressure. Okay, so the volumes are being cancelled. The final pressure would be equal to 4,460 millimeters mercury. You will take note that when the volume is decreased, the pressure is increased. That is what it meant by inversely related or inversely proportional. The second law that we need to understand is the Charles law. Charles law tells us that the volume and absolute temperature of a gas are directly related at constant mass and pressure. Directly related or directly proportional, which means to say that when the volume increases, the temperature also of the gas is being increased. Okay? Which gives us the equation of Charles' law, which is volume or V1 all over temperature 1 or T1 is equal to V2 all over T2. This is an illustration of the relationship between volume and temperature. At the first picture, it shows us the volume of a gas at a temperature equal to about 250. Okay, and you will see in here the volume, which is about at the middle of the container at a temperature of 250 Kelvin. You will also observe that heat is being added or introduced to the system, and you will notice at the final condition that the volume is increased and the temperature also is being increased from 250 Kelvin to 500 Kelvin, meaning to say that the temperature was increased because of the introduction of heat. And you will also observe that the volume is also increased. This proves us that the volume and temperature are really directly related or directly proportional. We have here a practice problem which says a sample of a gas occupies 3.5 liters at 300 Kelvin. What is the volume that it will occupy at 200 Kelvin? So the initial conditions are 3.5 liters. That's our V1. Okay. And 300 Kelvin is our T1. We are asked to compute for the volume if the temperature is decreased from 300 Kelvin to 200 Kelvin. Okay. We have also a third problem which says if a 1 liter balloon is heated from 22 degrees Celsius to 100 degrees Celsius, what will be its new volume be? Okay, so in this problem, you have 1 liter balloon, that's volume 1, at a temperature of 22 degrees Celsius. The temperature is increased, so what happens to the volume of the gas? So in here, you would see that the temperature is increased, so we would expect that the volume will also increase. Okay, so in the first problem, which is marked number 2, the volume is 3.5 liters, the temperature is 300 Kelvin, and we are asked to compute for the final volume if the temperature is decreased to 200 Kelvin. So using the equation V1 over T1 is equal to V2 over T2, it's just a simple manipulation of equation again. We divide this side of the equation and then we multiply the denominator of this of the or the temperature 2 at the other side of the equation. It will give us an answer V2 equal to 2.3 liters. And for the next problem, we are given V1 equal to 1 liter and a temperature of 22 degrees Celsius. Okay? And 22 degrees Celsius was converted in terms of Kelvin, that is 295. Okay? V2 is unknown, T2 is equal to 373. So by using the equation of the Charles law, it would give us a volume 2, okay, equal to 1.26 liters. Okay. We have in here another sample problem which says a sample of carbon monoxide gas occupies 3.20 liters at 125 degrees Celsius. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? Okay, so we have 320 liters, that's V1, and T1 equal to 125 degrees. V2 is equal to 1.54 liters, and we are asked to compute for the final temperature. So T2 is being asked or computed. So the given are, okay, the temperature is converted to Kelvin, and we are asked to compute for the final temperature. And using that equation of Charles' law and by simple manipulation of the equation and substituting the given in the problem, you will be able to find out that the final temperature is equal to 192 Kelvin. You will observe that the volume is decreased from 300 or 3.20 liters to 1.54 liters. Okay, so it was decreased. So you would expect that the temperature will also decrease because volume and temperature are directly proportional. The third gas law that we need to understand is the Galos X Law. According to the Galos X Law, the pressure and absolute temperature of a gas are directly related at constant mass and volume. So previously we discussed the Charles law wherein he was able to relate volume and temperature. They are directly proportional. Same relationship applies to pressure and temperature being studied by Gay-Lussac. If the pressure increases, the temperature also increases. In the Galos X Law, we have P1 over T1 equals P2 all over T2. You may actually use the equation of Charles' law. That's a Charles' law problem, but we use the equation of combined gas law to solve it. All Charles' law problems can be solved using the combined gas law. The same is true as Boyles Law problems, and Galos X Law problems can also be solved by the combined gas law equation. In here you have volume 1 equal to 100 ml and pressure 1 equal to 150 kilopascal. V2 is unknown and P2 is 200 kilopascal. Pressure and volume are compared in this problem. So I think we have in here a Boyles law problem, but using the equation of the combined gas law. In the Boyles law, it tells us that if the pressure increases, of course the volume decreases because they are inversely proportional. Using the equation of the combined gas law, temperature is taken as constant, so you can cancel the temperature, and substituting the given in the problem, you would have volume 2 equal to 75 ml. The pressure is increased from 150 kilopascal to 200 kilopascal. Therefore, it is expected that the volume will decrease. So you have from 100 ml, it became 75 ml. Another problem, a gas occupies 7.84 centimeter cube at 71.8 kilopascal and 25 degrees Celsius. Find its volume at standard temperature and pressure. So we have V1 given in the problem as 7.84, P1 to be 71.8 kilopascal, and T1 equal to 25 degrees Celsius or 298 Kelvin if you add 273 to 25 degrees Celsius. V2 is unknown, and since it is stated that the STP or the final condition of the gas is at standard temperature and pressure, so we said a while back that pressure at standard temperature and pressure would be 101.325 kilopascal and a temperature of 273 Kelvin. So we have here a combined gas law problem wherein pressure, if the pressure increases, temperature should decrease and the volume should decrease. We are asked to compute for the volume too, so we would expect that volume should decrease. Using the equation and substituting the given in the problem, you would have a volume 2 equal to 5.09, wherein from 7.84 centimeter cube, the volume is decreased to 5.09 centimeter cube. Another problem, a gas pressure is 765 torr at 23 degrees Celsius. At what temperature will the pressure be 560 torr? Okay, so we are asked to compute for T2, okay, and with the given pressure 1 equal to 765 torr and T1 equal to 23 degrees Celsius or 296 Kelvin, and we are given a final condition of 560 torr, the pressure is decreased. According to our relationship on our Galos X law equation, if the pressure decreases, temperature should also decrease. Using the equation of the combined gas law, volume is taken to be constant, and so temperature is equal to negative 47 degrees Celsius. Okay. Let me check if we are getting correct answers in this slide. So we have 560 times 309 divided by 765. Okay, so we have 226 Kelvin, and since the original temperatures in terms of degrees Celsius, so we subtract 273, it would really give us negative 47 degrees Celsius. It is negative because the temperature which was originally in Kelvin is converted to degrees Celsius. Lastly, let us try to discuss the ideal gas law. Ideal gas law tells us that the product of the pressure and volume is equal to the products of the moles of the gas and the temperature and a universal gas constant. Now, I want to emphasize that there is no such thing as ideal gases. When we say ideal gases, these are gases that obeys the gas laws. They exactly obey the gas laws. But there is no such thing as ideal gas. All gases are real gases. No gas follows the ideal gas law, but we are studying the ideal gas law as a basis in understanding real gases. Okay, so to understand gases or using the ideal gas law, uh, the idea of the ideal gas law, it tells us or it introduces us to a new constant, which is the universal gas constant, which is a value of 8.3145 joules per mole Kelvin. Okay, or that's equal to 0.0821 liter atmosphere per mole Kelvin. So these are constants. The values of R varies depending on the conversion of the units being used. So these are different uh, values of the universal gas constant in different units. Okay. Now let us try to use the ideal gas law. Let us understand the ideal gas law using this problem. Calculate the pressure in atmospheres of 0.412 mole of helium at 16 degrees Celsius and occupying 3.25 liters. So the first thing that you need to do in any problem is to identify the given physical quantities in the problem. So we have pressure, okay, which is unknown. We have the number of moles of that helium gas, which is 0.412, okay. Now, the number of moles of a gas is being computed using the mass of the gas over its molecular weight. Okay, so if you have the mass of a gas divided by its molecular weight of that gas, it would give us the number of moles. So when we say moles, it's the mass of the gas over its molecular weight. The molecular weight can be computed using the values specified at the periodic table. Okay, so in here we don't need to compute for the molecular weight. We are not given a mass, so we don't compute for molecular weight. It directly gives us the number of moles of the gas, so we can use it directly. Okay, and then we have also temperature, which is 16 degrees Celsius converted to 289 Kelvin, and the volume of the gas, which is 3.25 liters. We will be using the universal gas constant, which is 0.821, because you have here in the unit of the universal gas constant, it has the unit of liters, atmosphere, and mole. And you will see later on that it is also consistent with the unit of the temperature, which is Kelvin. Okay, so using the ideal gas law equation, PV is equal to nRT, we just need to manipulate the equation. We divide both sides of the equation by V. So in this side, the V will cancel out. So we would have an equation equal to P equal to nRT over V. Okay, which will give us a pressure equal to 3.01 atmosphere. Again, okay, if you substitute the given in this equation, you will have this. To find for P, we need to divide the other side of the equation by 3.25 and the units will cancel out, leaving you the unit atmosphere, okay, which is the unit of pressure. Another example, we are to find the volume of an 85 grams of oxygen at 25 degrees Celsius and 104.5 kilopascal. Instead of the number of moles, we are given the mass of the gas or oxygen to be 85 grams. Okay, so we're given the volume is unknown, N is 85, T is equal to 298 Kelvin, P is equal to 104.5, and we will be using the R equal to 8.315 uh, decimeter cube multiplied by kilopascal over mole Kelvin. Using the ideal gas law, you will see in here that the number of mole is computed. The 85 grams is multiplied by the molecular the molecular weight of the gas, or divided by the molecular weight of the gas. Okay. Now, 85 grams, okay, is being converted to moles. Okay. So the oxygen is diatomic. In the periodic table, it will give you the mass of oxygen to be 16. But since oxygen is diatomic, we multiply 16 by 2, so you have here 32. Okay? Yan. So, this is the molecular weight of oxygen. It's 32.0 grams per mole. But since we are given a mass, we multiply 1 mole over 32, or you divide 85 grams over its molecular weight, as what I've said a while back, okay, to get the number of moles of that gas. So multiplying the molecular weight, the inverse of the molecular weight, you would cancel the grams on the numerator, and to that of the denominator, it will give you a unit of moles. So 85 divided by 32 is 2.7 moles, which means to say that an 85 grams of oxygen is equivalent to 2.7 moles of oxygen. So we are now ready to compute for the volume of that ideal gas. Okay, so PV is equal to nRT, V is unknown. Substituting the given in the equation, you will have a volume equal to 64 decimeter cube. Okay, so that's all. We have discussed the different gas laws, namely Boyles Law, Charles Law, Galos X Law, Combined Gas Law, and the Ideal Gas Law. We have also discussed the properties, the characteristics of gases, and the physical quantities being compared in the study of gases, or in understanding gas laws. So I hope you learned something today, and have a great day.